Well, good afternoon, and welcome to Lecture 5 of Physics 2820. We're going to tackle two-dimensional trajectories today. So we've been dealing with a prototypical problem of a falling ball. We're going to extend that, and we're going to start to put in more dimensions, make things move up and down and left and right at the same time. So that's the idea. As is the plan, hopefully you've logged in using that link provided within the D2L shell. It's important to use that link every time because that downloads and updates new material that I would have posted this morning. So in particular, lecture number 5. So let's start by shift entering on that to get the modules all running all the way through. I want to talk about projectile motion. So here we go, projectile motion, right? This kind of idea. You'll have some sort of initial velocity and it'll fire something, and the path it takes is what we typically call projectile motion trajectory. And of course, the way that this works, as you remember from first year physics or high school physics, is the velocity in the vertical direction experiences acceleration due to gravity, and the motion in the horizontal stays constant because there's no forces acting in the horizontal. In terms of Newton's second law says that the mass times the acceleration equals the forces acting on an object. And so what we can see is that we have no force acting in the horizontal and we have a force acting on the vertical, and that's about it. The technique we're going to use to model all of these differential equations is to rewrite systems of second-order differential equations as systems of first-order differential equations. What that means is we take each one of these second-order derivatives and we turn them into first-order derivatives. And two of the derivatives are very simple. They just say the derivative of x with respect to t is exactly the velocity. The derivative with respect to y with respect to t is exactly the velocity in the vertical direction. So there's no thinking here. You're just taking those two equations. They become this equation, and we insert two more. That gives us a system of 4 equations and 4 unknowns. The application of Euler's law is the same, or Euler's method. We rewrite each and every one of those derivatives in terms of a finite difference, and then solve for the velocity or the position at the next time step all the way through. Now the masses cancel. They don't come into play in this first easy problem. The idea of this notation, xi plus 1 equals xi plus vxi, what it's saying is the position at the next time step will be equal to the position at the previous time step, or the current time step, multiplied with the velocity at the current time step, times however big the time step is all the way through. These I plus 1s and i's are helpful, especially as we get to more advanced numerical methods, which may depend upon both the previous time step and the previous to previous time step all the way through. In terms of a notation, all that this means, xi just means evaluate the function at the time ti. Xi plus 1 means evaluate the function at the time ti plus 1, and so on and so forth. The idea being time, which is usually considered to be a continuous thing. It's broken up into a bunch of discrete points in time: the first time step, the second time step, the third time step, t1, t2, 3t, 4, t5, ti plus 1. That's the idea here, is we're figuring out what these functions are at discrete points. Now, like for a falling particle, if you're going to do projectile motion through the air, you're going to have air drag. And for any particle moving at even a moderate speed, that drag is going to be predominantly quadratic in its dependence on velocity. So what we can do is we can model it with an air drag term. That is, the force due to the drag of the air on the object is going to be proportional, that's what C2 represents, the square of the speed of the object. And importantly, drag always opposes the motion. If something is moving towards the right, then the drag is going to push it towards the left. If it's moving down, the drag is going to push it up. If it's moving at at right angles, at 45 degrees to the horizontal, then the drag will be 180 degrees away from that. Now you can take this magnitude and use the fact that it's always opposite to the drag and figure out, just from coordinates, what the components of this drag must be. Okay, so the idea here is I split this into components, cos and sine. I rewrite these things in terms of the angle which I know, and then I'm able to come up with these two things. So here's what I'm going to attempt. I don't know how well this is going to work, but I'm going to try and draw this out. So if I stop the share, and I go to share, and I go to a whiteboard, aha. Did everybody see that? Just someone in the chat say, yeah, that works, no problem. That's a great technology. Where is the chat? I lost the chat. I heard a yeah. Okay, no problem. Great. Okay, so we will take this and we will clear all my drawings. Okay, so here's what I want to sort of understand. If we have something moving in that direction, we call that the velocity. What we want to do is recognize that we're always going to have a drag force in the opposite direction, right? That's the idea of the drag force. The drag force is going to be opposed to it. I want to delete you. Go away. Okay, I won't wait like that. Oh, stop drawing. Okay, clearly my ability to use whiteboards is limited. Okay, so that's supposed to be in the opposite direction all the way through. Typically, we talk about the velocity vector having a certain angle, right? So you might come along here and say, okay, well, this is the angle, right? This might be the angle theta. The idea is the magnitude of this thing is proportional to the velocity. So there's the velocity vector. This is the drag vector. I don't know how well this is working, but we're going to get there. And what I want to do, of course, is I want to talk about the components. I want to be able to talk about the components in this direction and in this direction, right? So in terms of components, what we're doing is we're splitting this up, and we're recognizing that if I know the angle at which I'm moving, I can write this in terms of sines and cosines. The only other step in terms of understanding how to come up with this thing, let's go with some greens. If I have these two components, we would call these components, right, we call that Vy, we call this Vx, and we call the length of this thing the speed V. The cosine of the angle theta is equal to Vx divided by V. The sine of the angle theta is Vy divided by V. So that means we can figure out cosine and sine of this angle in terms of the ratios of these two things together. Okay, so there we go. There's a little sketch. That's the kind of thing I would normally want to do to draw out. I'm going to stop that share and go back to sharing the lecture. Right, and basically you get this kind of idea. You're getting that it's going to be related to the cosine and the sine, but it operates in the opposite direction all the way through. So that's pretty good. But I knew this. Just the chat. Oh, it's there. It's there. Okay, no problem. All good. Okay, so that's all it is. You can work that out again. And one of the things I'd encourage you to do with these lectures is as you go through them or as you're reviewing them, have a piece of paper nearby and just try and figure out how you would go from this step to this step. Make sure you can do that. Okay, so this is what we have now. If we have two new forces, that means from Newton's law, acceleration times the mass is equal to the sum of all the forces, the net force. So this is the formulation. This is the physics of the problem. Now you know how to do mechanics. You already know how to do mass times acceleration equals the sum of the forces. I'm just writing that out explicitly. One of the goals of this course is once we've formulated the problem, we've formulated what I'm calling the equations of motion, then I want to solve that problem numerically. And I'm going to review Euler's method again. Euler's method is sort of our prototypical numerical method. I want to make sure it's really clear what it's doing. What we're looking at here is a bunch of derivatives, and they're equal to stuff on this side. I call this stuff the right-hand side, right? So I can come along here. Let's see if I can do, right, all of this stuff right here. I'm going to call that stuff the right-hand side of the system of equations. To solve any system of differential equations with Euler's method, what we're doing is recognizing that it's a derivative on the left and stuff on the right, and there's always some initial condition. You need an initial condition, a starting point for any of these things. You need to know what the value of the function is at the first time step, the t0 time step. The algorithm, which is what we call Euler's method, is just to say, okay, well, I'm going to start at the first point and then iterate through time. I'm going to use this rule to figure out what the next time step is based on the previous time step plus whatever the value of the function on the right-hand side, which of course is just the derivative, but it's all of these things multiplied by the time step. This just comes from the finite difference of it. So that's what you should be thinking of whenever you go from this system of equations to some rule that's going to evaluate it all the way through, namely that guy right there. What you're thinking about is this numerical algorithm. So what we write is to figure out the new position in the horizontal coordinate, it's equal to the old position plus the derivative of the position with respect to time. That's velocity times delta t. To figure out the new velocity in the horizontal direction, it's the new velocity in the next time equals the velocity of the old time times the derivative of velocity with respect to time. That's an acceleration multiplied by the time. Okay, Kayla is asking a good question. Could you explain the algorithm again in relation to the derivatives? Okay, so this is, I'm going to keep on hammering this until we get it. I've got a derivative here. This is a piece of math, right? So this thing right here is something that in general you could solve mathematically. This f of y could be anything we like, right? So maybe in this case f of y over t is equal to 2 times t plus y. Okay, so maybe that's what it is for a specific case. What we're going to do to solve this problem is we're going to take this derivative and we're going to rewrite it out. We're going to write it out as a finite difference. We're going to write this derivative out as a change in y. I apologize, my ability to write on with a mouse is not so great. We're going to write the derivative not as dy dt, but as delta y delta t. And the idea is that's the difference between yi plus 1, as in the next value of y. Eraser. Minus sign, all divided by delta x. What we're imagining going on here, I'll just draw a little graph. If this is time, that looks pretty good. And I know the value of y I at t I. So let's suppose I know this point. And my goal is to figure out what the value will be at a later time, ti plus 1. All I'm doing is I'm approximating the function as a straight line with slope given by this function. Evaluating the slope right here of a function, the slope of a function is its derivative. And then what I'm doing is I'm saying, okay, I'm just going to go forward a time step of ti to ti plus 1, whatever that difference is. And that new point is going to be my yi plus 1. So the logic here is from this point, do a linear interpolation to come up with this next point. And then once you've done that, you have the new point. And you can continue on your way to figure out the next point, and the next point, and the next point, and the next point, all the way through. And that's what the method is doing all the way through. So if you rewrite this bit right here and expand it out, this is the rule that you come up with. Any more questions about that? And many of you do have mics, so if it's more helpful to jump on and ask a question with your voice, go ahead. Any more questions about the Euler method? Okay, clear that up, and let's continue. Questions are good. Questions are the way we learn. Okay, so we have a system of equations. It's just Newton's law. Rewriting this in Euler's method says this is an algorithm that's going to let us solve what's going on. Now, this algorithm, these forces due to drag depend upon the speed of the object, and that's what VI is. Okay, VI is not the components of velocity. It just is the speed. So when we talk about VI, what we really mean is the speed at the time ti, or that time step, and you calculate that, of course, with square root of vx squared plus vy squared. The thing about first-year physics When you remember doing this in Physics 1050 or in high school, one of the big tricks, one of the big techniques is you could treat this pair of equations and this pair of equations completely independently. You could solve for the vertical position and vertical velocity separately from the horizontal velocity and the horizontal position. We say that those equations are decoupled in first year physics. That allows us to solve horizontal and vertical independently. However, now, because of this guy, can you see how that term exists in both sets of equations? You can't solve one equation independently from the other set. You have to solve them both together. We say these equations are all coupled together, and that makes it more challenging. This is one of the reasons we're going to use numerical methods as opposed to attempting to solve this analytically or with pen and paper, blackboard and chalk. Okay, so let's do this. Let's write a program that solves this trajectory motion kind of problem. When you're solving these problems, don't start from scratch. The intention is not to start with a blank piece of paper, or in the case of programming, a completely blank file and say, I don't know what to write. Start with something you know. This is a projectile motion problem. It's related to a falling particle problem. So how about we start with the prototypical code that I gave you at the beginning of lecture 4 as a starting point. So I'll just reproduce it here. So this is straight copying and pasting of the code we started with lecture 4. So remember we had looked at the falling particle. The idea of the template or skeleton or framework or cookie cutter here I'm giving you, and these are all the programs I've been writing, is we need some driver code that's going to start the program, it's going to run it. It needs to do 3 things. It needs to sort of set up the model, set up the numerics it's going to solve. It actually needs to solve that, and then it needs to visualize it. The code that steps through it is called a stepper. And the idea of the stepper is every time this function yields, which just means if it's used in a loop, it's going to return back the state of the model, namely the time, position, and the velocity at every point in time. This idea of yield is because you use this function inside of a loop. So this is happening the first time, the second time, the third time, the fourth time. Every time through this loop, y, v, and t are being updated using Euler's method. And the idea of the yield is it's expected to call this thing inside of a loop. We talked about a couple lectures ago how to write a loop that did this. And what we learned was this guy right here, this idea of using pandas data frame, has inside of it a loop. What it's doing is it turns this model, this thing that's going to spit out every time you call it, t, y, and v, it's going to give you all of those things as 3 columns in something called a data frame. So it's a way of iterating through this model all in one go. Yes, there are other ways of doing it. You could, and I'm not recommending it, but you could create a list for t and a list for y and a list for v, and every time through that, you append to the end of that list. That is exactly what this is doing. It is just doing that operation without us having to code that up. A question from whoever MATLAB52 is. What does it mean to be a driver's code? Okay, driver code. Driver code is just the code that runs the whole thing, puts the pieces together. So this code doesn't actually do anything on its own. All it does is it puts the pieces together. It's something that drives the whole application. It could be called target code, the main application, the app. Any language like that is fine. A driver is something that drives the simulation. It controls it. It's a drive in the sense of a controlling application. It's going to set up the model. It's going to iterate the model, solve it, do it in time, and it's going to plot the model. It's the one we're going to call when we want to make this actually run. That's why we call it a driver code. Okay, and finally, we need a visualization. We need some way of looking at the output so we can see what's going on. As before, I'm going to remember to run this cell, and run this cell. So they're now all defined, and I can start by checking that default application worked. Okay, and that's the falling ball problem we talked about before. Okay, with that cookie cutter, and the idea is you can always go back and pull this out, you can start to write a new program that follows that same framework. So what I can do is say, okay, well, the first thing I'm going to need is some driver program, something to just get this to go. So I could take this driver program, looks like a perfectly reasonable framework or template or skeleton to build off of, copy paste it, make a new one, and it's exactly the same. The only change that I made is I'm not looking at falling particles, I'm now looking at projectile motion. So let's introduce some new names. Let's label this thing so I can be very clear what the projectile motion is, and I'll call it a projectile motion stepper and a projectile motion plot so I can make that work. Okay, before I continue on, Cassandra says, why didn't you have to put a plit.show in your plot function to show the graph? We talked about in Jupyter, the last element in any cell gets automatically displayed. That's true. What Jupyter also does is if you created a plot object, if you are using a plot object somewhere, it assumes you want to display it. That bit of magic of like, well, I didn't ask for it displayed. Why is it displaying it for me? Way back at the top of the program, we put in this little control. This is saying to matplotlib, the plotting engine, anytime I make a plot, I really would like you to show it to me. If we didn't put inline in, if we never typed that line in, then we'd have to be more specific about when we want to show plots and use plit.show to actually display the plot. That's why we don't have to type it in all the time. Okay, so here's my driver program. Now, why would I want to start with the driver program? I know that if I was to try to run this program, it wouldn't work. It wouldn't work because projectile motion stepper and projectile motion plot do not yet exist. So in fact, if I run this and then I try and run it, I will get an error. And that's to be expected because I haven't written the rest of the code. The reason I start with the driver code, the outermost code, is it allows us to do something called test-driven development. This is the program that when you eventually write this piece of code and this piece of code, you have something to run it right away and see if it worked. It shows you what things are still remaining that needs to be solved. Once all the bugs go away and there's no more errors, then this program will start to work. You can test it as soon as you're done. So let's look at one of those errors. Reading Python errors takes a little bit of skill because it tends to show you more information than you really want to know. Whenever you get an error in Python, it's going to dump a whole bunch of stuff to you in a red box. And the idea is you're reading through this and you're like, what does this tell me? Here's what it tells you. It's the thing at the end that you care about. That's the actual error you want to read to. Everything else above it is called a stack trace. It's just saying where the error occurred. But your eye needs to go right to the very bottom of the block to find out what the error actually is. In this particular case, it's a name error. It's just, and it's telling you, it's like projectile motion stepper is not defined. Okay, all it's telling you, reporting back, is I don't know what projectile motion stepper is. I don't know how to run this program. I've got to stop. These lines are telling you where the error occurred. It's on line 4 of this program. So if I scroll up, it is indeed the 1, 2, 3rd, 4th line of this program is where the error is occurring. So all of those are just to help you find where the error is occurring. Now, once we write a projectile motion stepper, a program to implement this error will go away. So let's write that. The deal about this projectile motion stepper is it's basically the same as the falling particle stepper, except for it has more variables. The original problem had a y and a v. We now have 4 variables. We have horizontal and vertical position and horizontal and vertical velocity. So let's add that. And what I mean by adding it is I would have started by taking this piece of code, copy pasting it, changing its name, and then beginning to modify it to suit. I need to add in an initial condition for x, an initial condition for the speeds. Initial conditions are needed anytime you solve differential equations. You need to set up those initial conditions so that you start at the right point all the way through. I need to talk about not just velocity, but Vx and Vy. So I relabel one of the velocities from just V to Vx and introduce a new one. Every time I take a step through this model, I want to see back all of the information, all of the state about the model. So I'm going to return not just t, but x and y, and Vx and Vy. I'm just adding things all the way through. Now, I know I'm going to eventually have to figure out this drag thing, but in the first go, the first time I'm running this, the drag is going to require some thinking on my part. How do I calculate speed? What do I do about the angles? So one technique is just to stub it in. Stub, S-T-U-B, that just means write code that will work, even though it's wrong. Write something as a placeholder that you will eventually fix in just to see if you can get the basic structure of the program working correctly. So I'm going to do it like that. I'm going to leave myself a comment to do as a reminder to me, the programmer, that I need to come back to this. But I know I need some parameters. I need a FDX and an FDY. And then I need to extend the Euler's algorithm so it's got all the pieces in there. I already had a line that looked like this. I need to add a new line for the horizontal. And then I need to also update the velocity. New velocity is equal to old velocity plus the acceleration times dt. Okay, so if I run this, now it's defined. I also need a very simple plotting program. For projector motion, the most natural thing that I can think of to plot is to plot the vertical position against the horizontal position. So let's do that. Our projectile motion plot is going to plot the x component on the horizontal, the y component on the vertical. Always give yourself some labels, and you're good. So with that cookie cutter and that driver code, I now can test my program right away. Okay? So when I run this, I can see whether or not I've made any mistakes. And there's a problem. I get a name error. So let's debug this, right? Let's make sure we understand what this means. There's a lot of stuff that comes up. Your attention, though, should go to the bottom. And the bottom says name. M is not defined. It's telling you where the error occurs. You started in projectile motion app. That was the outermost piece of code you were calling. That piece of code on line 7 called ball data frame. Inside ball data frame, it's looping through all of the different steps of the model. This code right here is in the internals of Panda, but internally, you see this word iterable? It's just stepping through it. Every time it steps through it, it calls motion projectile stepper. And on line 31 of that program, there's the actual mistake. So this is called a trace or a stack trace. It tells you how I got to that line to have the mistake. And it's saying on that line at the very end, the mistake is I, Python, do not know what the letter M is. So we go back to projectile motion stepper. And we go, okay, well, what's the issue? I don't know what M is. You know what? I just need another constant. I just want this to work. So how about I make it up here? And then you might think about it going, you know what? I might want to change that one day. So let's just pass that in as an argument. So I've modified the program so that now mass is defined. And now we rerun the program and we'll see if we're done. Okay, so now we don't have any syntax errors. This is getting better. Name error, she fixed now. So we fixed that. How to read Python error messages, we did that. And now we want to see whether or not the program is working correctly. So I want you to look at the code and think about what that program is actually doing, and does this make any sense? If I think about projectile motion, I would expect to see a parabola. What I want you to go and do right now is on your version of the code, change the default initial conditions on projectile motion stepper so that you get a projectile motion. a parabola appearing instead of this straight line. And then we'll come back and we'll talk about it in 2 or 3 minutes, okay? You try it, come to me on the chat or join in by voice if you have any comments or questions. Okay, thanks, Andrew. That's exactly right. You need to give it some initial velocity. Right now, we're just dropping the object so it falls straight down. If you give it some initial velocity, like you're launching it, you get a more classical projectile motion kind of shape. So I'm going to do that. I'm going to say, okay, let's change it so that we have an initial velocity. There we go. Now we're getting the beginnings of projectile motion. Now, when I think of projectile motion, I normally want to think of things being launched from the ground. So let's change it a bit more. Let's give it not only an initial velocity to the right, let's give it an initial velocity upwards. And let's start it not from 100 meters off the ground, but right from the ground all the way through. Okay, so you see the model goes up and down. Because in projectile motion, the code as we've written it starts at 0, shoots up, and then runs for a long time. And it runs until the program ends. Well, okay, let's take a look at this. How could I get this program to run for longer? I might be able to change the initial speed. If I change it from Vx and Vy to a 30, the program will fire longer and faster. There you go. There's the basic shape all the way through. So it's going up and it's going down. And of course, I wanted to touch the ground. I have to run the program for longer. The issue here is I'm stopping the program whenever Tmax equals 5. Let's run the program for a little bit longer. Let's run it to Tmax equals 6. And so now you can see you get this sort of stereotypical plot, which is a problem, which is what we're expecting. Okay, so once you've played with your model a little bit, you've changed the parameters, you're starting to get something that makes some sense. The next step, after fixing the syntax errors, the Python errors, and it looks approximately right, is to check it against a known solution. Do you have some analytical expression about what this curve should be so we can test our program to make sure we've done it right? Well, of course we do. We know from first-year physics, there is an analytical expression. In the case of no air resistance, you have the kinematic equations. You have the equations that tell us y and x is a function of t. If I solve the system of equations by eliminating t, I take this t, I solve for it, and I substitute it into this equation, then I can get the following equation. It's a parabola. This is the equation of a parabola in its full sort of set of details. So maybe to visualize this plot, what we want to do is plot both the solution and an analytical solution together, and we'll see whether or not this program, the one that's producing this plot, works at all. So I'm going to redefine my projectile motion plot. I'm going to make it do a few more things. Initially, this is all that it did. Now I'm going to add in a bit more stuff to it. I'm going to control the style so I can change what color it is. I'm going to make a legend an optional thing, and I'm going to attach a label to say this is the numerical solution. But this is all the stuff that I've added, which is new. What I need to do to figure out the analytical solution is I need to know what the initial conditions are. I need to know what this V0, Vx0, x0, I guess y0 as well, is in this expression. I have that information in the data set itself. Remember when we run this model, it returns back a data frame, right? The whole idea of these models is when I run the model, so if I say projectile motion stepper, I get back a model, and then if I turn it into a data frame, I can actually look at all those columns. We talked about previously that if you wanted to, well, maybe I can't remember if we talked about it. These have different rows. If you want to talk about a particular row, you use ilock, and that prints it all off. The very first row would be row 0. That first row, the values at time equals 0, those are the initial conditions. So let's use that information. let's get that very first row of the data frame, particle I lock 0. Let's pull out the initial position and velocity. And now that I know that, I can evaluate y at each and every one of those points. X is just all of the x values. And what I'm going to do is evaluate those things, not with the numerical method, but with an analytical expression. This is exactly the same analytical expression as what's up right here. And then I can plot it. The only other thing I'm going to add is, because I'm launching these things into the air, let's draw on the axis a horizontal line at ground level. And I'll show you what that all looks like. So here we go. Numerical and analytical, they're right on top of each other. This is fantastic. This means that we've got a really good program that we're able to model and able to use. Now, if you wanted to see a difference between these two things, maybe we'd want to introduce some sort of numerical error into the program. If you remember, the error in this program is really related to, I'm actually surprised it's working that well. It's working too well. I don't trust it. It shouldn't be the same. Should pump that up for a second. Okay, that's good. Wow, that's working even better than I thought. That's fantastic. Okay, great. Happy days. Okay, so we've got a nice model. It's consistent with the numerical results. It looks like this thing is actually working just fine. Yay. Okay, I thought we'd have another problem, but we seem to have done it correctly. Okay, at this point, let me take that projectile motion stepper code you had above that you modified, and I'm just going to copy and paste it down here again. You don't normally need to do this for your own notebook. I'm doing this so we all agree and have the same code. We've made the same changes. The only thing I'm going to do here is I'm going to add in some air drag. So I want to now modify projectile motion stepper. And I said, normally you just edit the code. I want to add it so that we're also having air drag in the system. I add that variable for air drag. It's some default value. And what I want to do is I want to figure out the lines of code needed to calculate drag. From our physics understanding of it, we know we're going to need the speed. Mathematical operations like cosines, sines, square roots, exponents, they live within the numpy package space. So numpy.square root of the current speed, of the current velocity components and the magnitude of it. I use our equations to figure out what the force is all the way through, and then I can plug that and leave this code exactly where it is all the way through. And let's take a look at how this all works. Oh, okay, well, this makes sense. Because I have drag in the problem, my numerical answer is not going nearly as far as my analytical answer, because I'm slowing the thing down, right? So if you went back and you changed it so that C0 is equal to 0, they would match up exactly right. Or we could put drag back in and it wouldn't quite work. Now, this idea of editing the code and rerunning it, it's an approach. I happen to like the idea of writing interactive widgets so that you can explore the behavior of these models. What I want to do is I just really want to change this number. I want to see how the model behaves as I change this number. So let's write a new driver program that solves that problem, right? So I'm going to write a new driver program. I'm not going to try and make one master driver program that does everything I can imagine. I'm going to write them for specific purposes. This application is going to vary the drag coefficient. That's its entire job. It takes as a parameter a drag coefficient. By default, it's 0, but I'm going to change that. It needs to set up the model, and I'm just going to pass in whatever drag coefficient was given to me on the outside, solve it, and then plot it. And then what I can do is I can wrap that in an interactive. We talked about these widgets. What this is doing is it's running this program with the argument C2 that start from 0, go as high as up to 0.02, and change by a step size. And so what that gives us is a nice quick little routine where I am controlling how far it went. Now, to understand a few things about this code, the reason the analytical solution stops is because I only solve this problem until it's for every point of numerical x, I solve the analytical one. So that's why it stops right there. I've gone and I've made a few other small changes to the code. Before, in the original version of the code, this if that says if y is less than 0, set in 0, I'll put that back in, you'll see what happens. See how the code goes up and it goes all the way down? I added in some logic that said, run until the maximum time occurs, or the object hits the ground. That's another situation where it can stop. So if I put that stopping condition in, then the program will end whenever y becomes less than 0. So we've got a nice little program here we can vary. Sometimes you've got to play around with how you run a visualization. This command sets the limit in the horizontal direction. Let me comment that out to show you what would happen if you didn't have that in there. Looks the same, no problems there, but now let me advance this through. Can you see how picture's changing? But what's jumping around is the scale, 0 to 80, 0 to 60, 0 to 160. When you have something like that changing, even though the shape is changing, the scale is also changing. It's helpful, especially in these animations or ways that you're comparing data, to keep the scales the same. And so we can control the scale. And I can say, for this particular application, how about we always show 0 to 200 meters? So then, doesn't matter how I draw this thing, it's on the same scale all the way through. And we can see the effect of drag on this thing. And not surprisingly, if you add in drag, things don't go as far as they would normally. Okay, so what I was trying to demonstrate here is a technique or a strategy for modeling these kind of problems. And where I want to finish off the second half of today's lecture is I'm going to take some exercises straight from the textbook. These are the kind of things that I would put on an assignment, and I want to do some assignment questions with you. Okay, so in terms of the assignments, we've already talked about a few questions. I just posted today assignment number 2. These are questions we introduced in class. These are taken straight from the textbook. So hopefully, or maybe, the relevant section of the book might be useful in doing them. But the idea is to write programs and commentary that answer these questions all the way through. There's 2 problems I have due for a week and a half from now. You are currently working on assignment 1 for me. What I'm going to do is I'm going to give you this problem right here, problem trajectory of a steel ball. And this is a problem that will appear on assignment number 3. But what we're going to do is together, we'll do part A. Hopefully we'll get through part B. And then I'll have you do part C on your own as part of assignment number 3. So let's walk through how I'm suggesting you tackle these kind of assignment questions. So here's the question. We're looking at the trajectory of a steel ball. Compute the 2-dimensional trajectory of a ball moving in air without air friction and plot y as a function of x. Oh, that's what this lecture was about. That's interesting. The professor is asking me to do something that I did in the lecture. Exactly. I want you to do that again. What do I want you to do with this thing? I want you to compare your computer results with the exact results. Well, that's sort of like what we were doing right here. And it says, for example, assume the ball is thrown from ground level at an angle theta 0 above the horizontal with an initial velocity of 15. Okay, so for this problem, the speed is always going to be 15, but we're going to play around with the angle. That's going to be the parameter I want to change. And what we're asked to do is vary this parameter and show that the maximum range occurs at 45 degrees. What is the range, Rmax, the maximum range, the distance it travels, that point right there at this angle, and compare your result to the known analytical quantity of v² over g. Okay, so I need a program that does this, that sets this thing up. The way that I would approach it is I would start with one of the sample applications we've got. We've already got code that models projectile motion. You can just take the projectile motion stepper, copy and paste it straight into your assignment, you're done. What I need though is an application to drive this, to answer this particular question. So let's go back up, okay? And I'll just pick some code. Okay, I'm going to pick this piece of code. It sounds like a good skeleton or framework to build upon. I don't want to vary the drag coefficient. I'm going to vary the angle, but it gives me the right idea. So I'm going to start with that piece of code. Okay, now I want to give this thing a name. You could come up with a clever name if you wanted, but if you just wanted a boring name, that's okay too. This program is going to solve problem 310 part A. So let's call it problem 310A app. What is it going to do? It's going to vary the angle. Now, you don't have to do this, but we could use either the word, like we could just say angle as a word if you don't want to use Greek letters. And how about we start this thing off at an angle of 45 degrees? That sounds like a good starting point for this program. What I need to do is I'm going to have to set up the model. I don't want any drag at all in our model. I want to have to specify an initial velocity. And initial positions. Okay. And I have to sort of figure out what the code needs to be. Let's just put it as, I don't know. No, I don't know what it would be. I'll put a 7 and a 7 here as a stub, just something to try out. I want to iterate that model, and then I want to show what the solution would look like. And what I want to do as an application is I want to vary, for this problem, 310 app, I want to vary the angle. Well, what are good angles? I want the angle to be as small as 0, as big as 90, and let's do this in 5-degree increments all the way through. And now we check. We see whether or not this program works at all. Okay, got a bit of an error. Projectile motion stepper got an unexpected keyword argument. So this is an example of a type error. It's not a name error, it's a type error. Getting errors is common, and you need to learn how to debug these things. What it's telling me is, I used the keyword argument in a function vy, and it didn't know what that was. Where did the error occur? It occurred on this line, line 6 of this function, and it's a bit tricky. Even though it says it occurred on line 6, you can see that it's actually here, vy. What Python is doing is it's taking those 3 lines and telling you where the bracket is at the end. The error is occurring in this area. And there it is right there. The argument isn't vy, it's vy0. So let me go back to here and make that edit. Make that fix, and then check it again. So I rerun the application. Okay. It doesn't seem to do very much, but that makes sense because I'm not actually using the angle. But I've got at least a test program that I could work with. Well, what I need to do is, I'm told in the problem, I need to have an initial speed of 15. We're told to always use an initial speed of 15. I need to somehow figure out what the initial components of the velocity need to be. I need to write the code that makes this work. And so we have to try to remember or figure out or ask a question. I need to know what line of code would give me the components of something that had this angle all the way through. Well, if you remember, converting a magnitude and an angle into components, I've got to multiply by n pi times cosine of the angle and n pi times sine of the angle. Okay, so now I've written some logic that given an angle, I'm calculating the components of what's going on here. Now I can test it. Okay, so as I run this thing, that doesn't look so promising. That looks pretty broken, actually. That's not working. Okay, let's try and figure this out. First thing, this horizontal axis. Maybe I don't want to say it goes to 200. Maybe that's not appropriate for this problem. So let's get rid of that. Okay, here we go. It's launching up. It's going down. Everybody's all pretty happy. 50. It looks like it's shooting down into the ground. 55. It looks like it's really shooting into the ground. 60. It's going backwards. I don't know if you can see this, but it appears that it's starting here and being launched towards the left. Look at X. It's negative. Let's go back to our code and try and understand this. We are trying to understand why this velocity is not doing the correct thing. I have an angle of 45 degrees or 65 degrees or whatever, and I want to make this work. Why am I not getting a proper plot all the way through? Well, we might need to do some debugging. There's a few ways of doing debugging, but sometimes the easiest way of doing it is just to give yourself some informative print statements. How about we, when we run this program, tell ourselves what the coordinates are. And if you remember how to do format strings, what this will do is while running the program, it will spit out the string vx0 equals something, vx0 equals something, to let us know where the error is. Okay, so I've got an angle of 7 and 12. Oh, a couple issues here. One is that sure is a lot of decimal places. You might need to look back to another lecture. You may need to look on the web. You may need to look at how to format these things. We have covered it before, but let's do things to 2 significant figures or 2 decimal points. They're both floating point. We run it. These 2 numbers are not the same, but my angle is 45 degrees. These 2 numbers are not the same. That's weird. Okay, let me increase the angle. Oh, well, look at that. Negative velocities. It's like the angle that I want 60 degrees is much, much bigger than 60 degrees. What could be the problem? Now, some of you, if you've done this kind of thing before, you know what the problem is. Others may go, you got me. I have no idea why that isn't working. This looks perfectly fine. This is the kind of thing you send me an email, but you figure it out. You ask Kyle in the lab. You ask me in the lecture. You send an email. You put it on a discussion forum. Or you look up the documentation. The documentation, if you remember, if I go to this thing and then I press the character Shift and then Tab, it pops up what a cosine is. And here's the relevant line. One of the things you need to know about programming languages is they don't use degrees. They use radians, like a calculator. The number we pass in here is not supposed to be 45 degrees. It's supposed to be something in terms of radians. That's the problem. We're not launching this thing at an angle of 45 degrees. We're launching at an angle of 45 radians. Oh, okay. Well then, let's change it. Let's figure out what the angle is going to be. And again, I'm using this trick of \theta, tab, to give me a theta. I'm going to say theta 0, the initial angle, is angle converted. Now, you could, if you wanted to, try and do whatever thing, formula, try and figure it out. But almost everything you want to do in mathematics is inside the NumPy library, including a wonderful function that converts degrees to radians. And you may say, how am I supposed to know that? Well, 2 things. One, you didn't need it. You could have just divided by 180 and multiplied by pi and figured it out yourself. That's all this function does. And the second thing is, you just learned it. So this is the experience of learning these things. There's millions of functions, and over time you pick up more and more of them. And so one of the ones that's helpful is degrees to radians. Again, Shift Tab tells me what it does. It converts angles from radians to degrees to radians. So if I put in the word angle, this now becomes the value in radians. And that's something that I can copy and paste You hear? Here we go. Now I have a test program. An angle of 45 degrees is indeed 1061 and 1061. So if I increase the angle, it gets steeper and steeper. If I decrease the angle, it gets shallower and shallower. That makes sense all the way through. It is jumping around a bit, so let's put back this line so that the plots are always the same. That's a very shallow angle. Oh, that's funny. Plot isn't what I'm expecting. Just not drawing the whole way. Okay, 0 to 15. So it's showing that plot all the way through of a nice picture so we can see what's going on. Okay. Kayla asks, I'm sorry, could you please go through that angle change again? Okay. Angles can be measured in degrees or radians. There are 360 degrees in a circle. There are 2 pi radians in a circle. The mathematical operations, cosine, sine, tangent, like on calculators, on programming languages, is almost always in radians. So we have to convert the angle 45 in degrees to radians first. There's a function inside NumPy called degree to rad. And the idea here is degrees get converted to radians. You pass in any number of angles and you get back the value in radians. And that's what I'm going to pass to cosine all the way through. I need to do that so that I can still think in angles, but the code will work in radians. This function, all that it does is it converts degrees to radians according to the sort of normal formula. Okay, the formula is just x times pi divided by 180. That's all that it's doing. The documentation explains exactly what it's doing. It's very complicated because it works for generic arrays of any shape, but that's all that's going on. So it's just converting degrees to radians. Okay, so we're going to continue. Now we have a program. I get to vary it. Let's see how we're doing in terms of the question. Compare your results with the exact results. They compare well. I think we've accomplished the first 2 parts of that question. Vary the angle and show the maximum range occurs at 45 degrees. Okay. Okay, well, so that. Oh, I know why. It's the heights changing as well. Not 30. How about we try I don't want to debug that in front of you because there's something a bit strange about how the view is going. It has to do with the aspect ratio. Not important today, but we'll get there. Okay, so we have the ability to vary the plot up and down. What I want to add to this is I now want to add something that computes the range of this thing. Now, we know that there is a theoretical result for Rmax. We're told in the question, V0 star star 2 divided by G. This expression, which as the question is the analytical result for it all the way through. Let's draw that on this picture. How do I draw it? Well, what I can do is make a plot of a vertical line at that location. Okay, so this point right here is the prediction of where the range would be purely from a theoretical point of view. This is the maximum range over any angle. And you can see that what happens as I get the angle more steep, it moves further away. If I move the angle to 45, it hits that point. And if I make the angle less shallow, it doesn't go as far again. So this is a pretty good way of sort of exploring what the difference is. Even better though, I'd love to know what the range actually is. What we're looking at right here is a graph, and I can sort of see that it gets close and gets further away. What would be better is to actually print out what the range needed to be. So here's what I'm imagining. Imagine you have code here. Determine the range, okay? And I'm going to stub it in. Put in some dummy value that's not accurate. Maybe we'll do this one. Maybe we'll do 20. Okay, I'll just put in some number for the purposes of playing around with it. I'm going to draw on my map, on my graph, another line that represents it. And maybe what I will do is put some text that say the range is this and R max is equal to yeah, there we go. So now every time I run this program, you can see how R max and R change. Now this is stub code because it doesn't work yet. This R20 is just hard coded. I need some lines of code to figure out where this point is right here. Well, if I'm going to go about debugging this, I'll probably want to zoom in on this region a bit so I can really see what's going on all the way through here. So let's do something else. Let's change the limit so that when we're dealing with this, I'm going to go back to this example of 45, I'm really zoomed in this corner so that I know what's going on. So what I'm going to do is I'm going to look at the points 20 to 25. Oh, and split y lim 0 to 2. Not 20, 2. This lets me control my field of view. Okay, why is my field of view not being controlling? Something I skipped over. By default, that's the field of view. It uses something called auto to set the aspect ratio of plots. There we go. 0 to 25, 0 to 2. That's working correctly. 20 to 25, 20 to 25, 0 to 2. What Axis Auto is doing is controlling the aspect ratio of this plot. Somewhere in one of these plotting routines, I hit dumped in, and I forgot to mention it to you. This line says split.axis equal. That changes the aspect ratio, that is the ratio of the vertical to horizontal shapes of a plot, so that circles are still circular, or 45-degree angles are still 45. Let me show you what I mean. I'm going to turn this off for a moment, and I'm going to ask you a question. Is this angle, you can imagine from here shooting up, is that a 45-degree angle? It doesn't look like a 45-degree angle to me, even though we know the angle is 45 and the components are 10 and 10. The reason is the shape of this figure isn't square, isn't equal. There are 6 units in the vertical and there are 20 units in the horizontal. It doesn't have a square equal aspect ratio. If I make the aspect ratio equal, what that will do is adjust the limits so that one step in the vertical is equivalent to one step in the horizontal. It makes lines that are 45 degrees appear 45 degrees by stretching things in the vertical. That was what was causing my things to look all funny. I'm going to go back to sort of the normal case, and now I'm able to actually zoom in on a particular region. So let's do that. Apologies for the sidetrack. Let's zoom in on this stuff right here so we can figure out what's going on in this part of the program. Okay, so I'm going to go into this region, and I'm going to do that by changing the y limits so it goes from 20 to 25, and I'm going to look at the region -1 to -2, -1 to 2. You can sort of imagine it being a zoomed in region right there all the way through. Okay, so we've zoomed in on that region and we can start to see a little bit more about how this program's working. Now, the line I'm drawing is the theoretical answer for where the maximum range is. And indeed, you can see this blue line right here It'd be better if it wasn't blue. Let's make it red. Yeah, you can see that that theoretical line is crossing over exactly where the analytical solution touches the ground, which is exactly right. What I want to do is figure out what the range is of my numerical answer all the way through. I want to write some code to figure out what this point is right here. Let's zoom in even more. Rather than from 20 to 25, let's go from 22 to 24. And in the vertical, let's just go from minus 0.5 to 0.5. So I'm zooming in to this box so I can see things more clearly. Oh, I typed something wrong. There, fix that. Okay, I want to figure out what this point is right here. That's my goal. All this is just code to help me sort of do that. Determine the range. Here's one way of determining the range. The points are just the coordinates x, and I want to take the largest one. So I could say max of ball.x. That would be a way of figuring out how far this goes. It's the largest possible x in my data. And that's not bad. That puts a line right here where the data ends. But you can see that we've actually got a bit of a problem. We've gone too far in the data. Now, I want to make sure this is clear. So what I'm going to do is I'm going to change the style of my plots so that you actually can see the dots where the values are actually evaluated. Do you remember how I said it takes steps? What we're doing in an Euler's method or a numerical method is we're using the value of the coordinates at this time to figure out what the coordinates are at this time. Then we use the value of those points to figure what the value is at this time. Then we figure the points of this one to figure out the points at this time. And we had a check, an if statement that said, if y ever got less than 0, stop running the program. So this is really why the last point is below the horizon. I don't want that point. I want this point, that point where it crosses. Well, what I could do is I could use this idea of talking about the particles, and I could figure out some point in between there. So one idea is just to take the last point and say that's pretty close. But we can do better. One thing is use max to determine the range, question mark. That's not so good. Another approach we could use is take the last 2 points and maybe take the average of those. Maybe that would be closer to where it is. Use average of last points. Maybe this will be a better idea. Well, that way of doing it, what we need to do is take a look at the last point in the list of the data, its x coordinate, and the second last point in the data, and the x point. This idea of iLock is this is going to the last row and the second last row. If you take those two values of x and I average them together, that'll be an approximation for the range. And you can see that now we're doing pretty good, right? It's sort of right there. We're doing a pretty good approximation. But if I was to zoom in even more, so if I was to zoom in to 22.75 and 23.25, and I was to zoom into -1 and -1, so I'm really zooming in on this point right here. You can see that there's a slight discrepancy between these two things. This is more clear if the angle isn't 45, but the issue, let's go back to this one here. Oop. Valid syntax. What did I do wrong? Oh, I stopped typing. Put that back. Yeah, so there's an example. So there's a situation when the angle's 40 degrees. Can you see how the line is halfway between this point and this point? But that means it's not still exactly right at that dot. we can do even better by linearly interpolating between these 2 points. The idea of a linear interpolation, okay, so this was an idea. It wasn't the best idea. Let's see if we can do better. Linear interpolation. The idea of a linear interpolation is basically, I don't know if you can see this in my picture. You see this thing, oh, right there, you see the animation I've got on there, my background? It's the equation of a straight line, right? We can use that idea that we know what a straight line is to figure out what it needs to be. There's the equation of any straight line. As long as you know the pair of coordinates x1, y1, and x2, y2, that's going to be the equation of the straight line. Well, if I'm going to do that, if I'm going to figure out the straight line that goes between these 2 points, I need to know the coordinates of those 2 points. Okay? So let's do that. Let's figure out the coordinates of the ball at the second to last location. Let's figure out the coordinates of the ball at the last location. So what I'm doing is I'm taking the records, I'm looking at the second to last row on the last row and picking out their x coordinates. And then I want to grab the same thing for y. So these are going to be the coordinates of this point and this point. Okay? You'll see that I did a lot of copying and pasting. That's a really nice way of getting your code done and mixing everything lined up, and you can make code pretty quickly. What I need to do is I need to take this equation and I need to solve for x. So basically I'm taking this equation and I'm rearranging it around so that it's not y as a function of x, but it's x as a function of y. Right? So this is just taking this bit, putting it on this side of the equation, or rather moving this thing to this side and flipping it around. And then what I want to do is evaluate at y equals 0. That will be the code. If I stick y equals 0 right in here, that will be the best definition for the range all the way through. So I'm just taking y and 0. These comments are useful because they explain where this thing came from. Let me show you how it works. Nice. Now you can see that this numerical result is going exactly through the point, the range that is, of where it touches the ground. If I change the angle to something a bit less, this line, which is the numerical result of the range, is exactly right. I can move back. Well, now that's out of my field of view. Let's get rid of these things because they were just there to help us out as we were debugging it. And we can see the overall graph. Even this overall graph isn't great because all of those dots, there's too many of them when we zoom out. So I'm going to go back to the style and just make them lines. And there we go. Now we've got a nice little program that we can iterate along to figure out how this program is going to behave all the way through. And what we can see from this is indeed the range gets close to the theoretical maximum at the point of 45. That's when they line up, and if you go anything bigger than that, it starts to drop down again. So this is a way of exploring this problem and comparing it to the analytical result by writing an application like this. Okay, what is it? It's 3:15 right there, so we're very close to the end of this lecture. I'm just going to do the following, and I'll talk about a second solution, but I won't go through it in the same amount of detail. Part B, suppose you've got a ball that starts at initial height h. So now it's not going to start from the ground, it's going to start from some h. How would the maximum angle, that is the 45-degree angle, change depending upon what your angle is? By what percentage would it change, the range change if you changed it by 2%? So what I'm going to do is I'm going to give you now a little block of code. I would go through the same basic operation of taking the previous thing as sample code and writing an application that's going to explore how the angles change. So this would be my solution to the problem. you'll see that it has some parts that are exactly the same, but instead of drawing the curve in this sense, you're worried about keeping up. I'm going to give you all of these, of course. I would never expect you to copy and paste all those things because you can't keep up. You're not supposed to peek up. It's all the way through. It's good. This is another way of formulating where now what we're going to do is draw it for several different angles all the way through. So let me show you that particular program. What I'm doing now is I'm making a visualization of range as a function of angle when the height is at 2. If I have a height of 0, then the maximum angle will occur at 45 degrees. But as I launch the thing from higher and higher up, you can see that the range as a function of angle starts to change. This is code that's showing you the derivative of the range with respect to the angle. And I've got another linear interpolation that figures out exactly what the maximum angle needs to be. So in terms of these two pieces of code, the question is, it's too hard to keep up. My hope is the level of detail I said out loud in terms of explaining how I wrote this program and how I would go through writing it in pieces, it has been helpful. If you like, and I'll wait for someone to tell me so, I'm happy to live code this block of code as well to go through it, or I can just sort of leave it as posted. Both of these two pieces of code will appear on assignment number 3. And what I want you to do on assignment number 3 is I want you to explore the effects of air resistance on this problem. But the idea was you would start with a piece of driver code and you would modify it and come up with a visualization to answer the question in the problem. Okay, so in terms of keeping up, you're not supposed to be taking notes on these lecture slides. The only time I'm really expecting you to type things in is when I pause to say exercise. I don't want you to be copying and pasting. That's not a useful use of your time in the lecture. Asking questions on the chat, that's useful. Asking questions with your voice is even better. And no one's tried to do that yet. And I'm not quite sure why you'd be willing to talk in class, but not willing to talk right now. So, am I right on the time there, Kyle? Is it 3? It's the end of the lecture period, right? Yeah. Okay, so I'm going to stop the recording here of this lecture, and we'll get into the lab.